Thank you.
Okay, hello everyone, and welcome to these seminars organized by UPM's Master in Quantum Computing. So our first speaker today is Helene Burghoff. She's a former student of the Master. She was with us the previous year, and she completed the Quantum Computing program last year. Prior to that, she was in a Bachelor in Business Administration, and she also has a Master in Software Design. She has several years of experience in project management in a fintech scale-up, and at the moment is working in Accenture in technology strategy consulting. And her thesis, the work that we will be discussing today, is focused on security and the quantum internet. It's in line with her efforts in Accenture, which she continues to advocate for an increased awareness in industry around post-quantum security and so on. Her speak today is going to be titled "A Review and Proposal for Security in the Quantum Age." So all yours, Helene. Thank you so much for being here.
Thank you, Rafa, for the introduction and for having me back. I'm really excited to be here again, and really hoping that, maybe some of you watching, either those in the call now or maybe watching the recording back, are also interested in the whole quantum security topic and can either find some inspiration or, if you have any questions, I'll leave my email at the end. Feel free to reach out to me. So that was already a pretty nice full round introduction, but just again about myself and kind of how I got into this track through the first master prior to the UPM program that I did was in software design, and there I wrote a thesis very related to quantum security and business analytics. So that's kind of how I slid into that. And yeah, as Rafa mentioned, still working on these topics now at Accenture, which is super exciting to see it from the industry side. So definitely what you're all doing is very relevant and very cool to see that from the industry side as well. So happy to also answer questions about that. A little overview, very brief and high level on what I even wrote my thesis about. I think it can be broken down into 4 sections, all of which I'll go into a little bit in the course of this presentation. Starting with the first section you see on the left there, the internet today. So I examined some security mechanisms of the common communication protocols and mechanisms that we use in the internet today, and how those present some vulnerabilities for quantum adversaries. The second section was looking into the quantum internet, so more directly related to what we're studying in the program and how security compares to that. So whether it actually offers some increased security over the classical channels that we're using nowadays. And actually, this is where the thesis got really fun for me and where UPM also allowed me to really dive into some cool topics, was discovering some flaws or some gaps maybe in research that is being done today, and also make my own proposal on infrastructure and security protocols. So kind of my whole goal with the thesis and where I was allowed to experiment a little bit and go down avenues that I really cared about was just raising awareness for the need of information theoretic security in our open internet, and encourage industry leaders as well as researchers to proactively think about the protocols and the infrastructure questions in the very early stages of the design for the quantum internet and the network there. So that's kind of the overview of what the whole goal and motivation was behind the thesis. And I do want to go a little bit into how I went into that, thinking that most of you are probably now, if I'm correct, thinking about what thesis you might want to write and which area you might want to go into. So I think this part is really relevant, and how also UPM helped me get some really cool connections and a network and exposure in industry about this topic. So looking at the security in the quantum age, with quantum age meaning both the current internet that is vulnerable to the quantum computers as well as quantum enhanced security in the quantum internet. In my prior research, I created a tool that automates the migration of web servers, specifically Nginx web servers, to post-quantum ciphers. I'll get a little bit into post-quantum cryptography in a little bit, but that was already on the classical side, where I felt like I wanted to create a tool that, just contributes something to this field of research. And I found that post-quantum cryptography is really exciting field of research, but actually we can do a little bit better by utilizing quantum cryptography and communications and the inherent properties of quantum mechanics. So that's why I ended up in this program, to learn more about that. And I don't know if you've already had the quantum cryptography and communications courses, but those are really cool if you haven't. And yeah, trying to find some better alternatives to the areas that I knew were vulnerable in our current channels. So specifically key exchange and identity authentication mechanisms, and looking at things like quantum key distribution, quantum identity authentication, that I found particularly interesting. And that's where I then was able to find this gap in research. And something I want to highlight here was that being able to talk with the professors and being able to tap into their network was something that was really valuable to me. First through internal discussions with my supervisor, Carlos, that we were bouncing back and forth ideas, but then also being able to schedule interviews with industry leaders in quantum communication and quantum cryptography allowed me to construct this thesis that really led the reader through the whole landscape of quantum security and the urgency of information theoretic secure mechanisms beyond just the QKD technology in an isolated setting. So all that being said, if you have any questions about the structure of getting to the thesis, or being able to tap into some resources in industry or in research that might be helpful for you, let me know and do reach out to me afterwards. And now to the actual nitty-gritty of what I even wrote this paper about. Basically, as I already mentioned, why conditionally secure TLS mechanisms aren't enough, and why I would argue that quantum mechanics can and should offer solutions for a more secure internet in the future. So, as you probably all know, the very basic communication protocols and mechanisms that we use today in the classical internet are based on the transport layer security protocol. And I looked at this to initially identify vulnerabilities, particular to quantum adversaries, of course. Not sure how deep you would have already gone into this, but I'll just give a brief overview. So the TLS protocol is incredibly user-friendly, it's scalable, it's efficient, it's a great protocol that secures our public channels and also is able to identify and authenticate users to each other's. So when the TLS protocol creates the initial handshake, you can see that sort of visualized on the right side of the slide. It allows a very flexible negotiation of the ciphers that are used, the algorithms used to encrypt messages between two parties. So the main aspects of the TLS handshake are the identity authentication, the key exchange, which allows to create the secret shared keys with which then the rest of the messages can be encrypted in a symmetric way. So those are kind of the three aspects, but particularly the first two, identity authentication and key exchange, are particularly vulnerable to quantum attacks. So the security of the algorithms in identity authentication and key exchange are basically based on complex one-way functions that are just too complex for computers of the current ability to crack. So with a quantum computer, obviously, that would be possible in minutes rather than decades. In fact, it would only take a couple thousand qubits, stable qubits, to crack a lot of the current encryption mechanisms we use. And at the Davos Forum, just, I don't know, it was 2 or 3 weeks ago, IBM mentioned that they would already achieve this sometime this year, which I guess is a bit questionable, but they claimed that publicly. So it's not far off that particularly these first two aspects of the TLS exchange are highly vulnerable and our communications will be compromised. So obviously something's being done about that, and I'm sure you have heard about the post-quantum cryptography initiative, you could call it, that's been driven by the National Institute of Standards and Technologies, but also other institutions, as you can see in the bottom left of the slide, that have been working towards suggesting algorithms, testing algorithms, trying to get a more secure way to update the TLS standard to something that's more quantum secure. So the NIST is actually expected to publish these new standards in 2024 already, but the problem is that even all the algorithms that are proposed here are still conditionally secure. So we assume that they're going to be more complicated to crack, and potentially quantum computers will also need more time or won't be powerful enough for another couple of decades to crack them. But the algorithms have been tested in this final round for years now, almost a decade even. They've been attacked by the cryptographic community to see if they're really secure, or if there's some way to break them after all. And only in August last year was the most recent of the finalists of the algorithms that was broken. by a single computational core computer, like a modern day computer, in less than an hour. So this kind of goes to show that not only do these computational complex problems not prove that they're going to be secure forever based on computational hardness, but there might also just be new mathematical ways to solve these problems found in the future. So we don't even potentially need quantum computers to be able to hack these mechanisms. So obviously there's a big issue, I think, around the way that we secure our data online nowadays. And I would argue that we would need better and more secure and provably secure ways to secure our data in transit online. So that's where my thesis went into the quantum enhanced security aspects, some of the things and the core concepts that we learned through the quantum communications and quantum cryptography course in the master. Primarily focusing first on the asymmetric key exchange mechanism that I also mentioned, if you think back to the little umbrella under the TLS standard. Obviously, there is the really widely hyped quantum key distribution technology. It's led to some of the biggest breakthroughs in quantum cryptography, and it basically allows two devices to exchange the exclusive secret keys. Thanks to the no cloning theorem, you can prove that no spy can sort of tamper or observe the message being shared without being discovered. So in principle, this provides information theoretic security in online communications, and it's great. It's so much better upgrade from the TLS public key encryption that we use. However, what about identity authentication? So this was a question that I asked myself when looking a little bit from a more higher level. We can use quantum key distribution to replace the public key exchange in a communication, but how do you confirm that the two parties talking to each other are who they say they are? Quantum key distribution doesn't address identity authentication at all. It's really only a way to enhance the security of a key, that like an initial seed that you've already exchanged. So obviously there's some big issues and vulnerabilities in that. So in the course of my thesis, I then looked at identity authentication enhanced by quantum mechanics. So currently the way that identity authentication works in TLS is that you have SSL certificates issued by some official certificate authority installed on your local machine. And these are exchanged at the beginning of the TLS handshake as well. As I mentioned before, they're also secured with public key encryption, so just as vulnerable as the public key exchange at the start. But I did learn that there is something called quantum identity authentication protocols that are being developed. Some of them are better tested, some of them are still pretty new, but they're basically another information theoretic secure way utilizing the properties of quantum mechanics to authenticate two parties to each other. And there's a bunch of different protocols that have been suggested. They all work very differently. If you're interested, I'm happy to provide you a list. I have it all researched in my thesis. But the one that was the most interesting to me was the trusted third-party protocols. So these are quantum identity authentication protocols that use a trusted third party in the middle, kind of like the certificate authorities that issue the SSL certificates currently, that would be able to authenticate two separate parties to each other in an information theoretic secure way. So that being said, these kind of classical as well as quantum enhanced security mechanisms in the online communications that we have today, I started posing myself a really interesting question, which was reading all these papers. Quantum key distribution is super hyped. There's many applications. There's early commercialization. You can already purchase quantum key distribution devices now on the market. But quantum identity authentication is very rarely discussed. And I actually also had a hard time finding a lot of bulletproof research on it. It was all pretty new and hard to come across. So I was wondering why that is, because quantum identity or identity authentication generally seems just as big of a barrier to ultimate security as the key exchange and the message sending. So this was where the thesis process for me got really interesting, because I got to talk to some experts in the field, to which some of the professors connected me. And I got to just straight out pose these questions to people that spend every day of their life doing this kind of stuff and looking into it. And this is where it got really, really interesting to me. So I was told primarily that there could be interest in expanding this application of quantum identity authentications, but information theoretic security is such an ambitious goal considering the state that we're at right now. Most companies in industry, and I found this to be true ever since I started working in industry now as well, don't even have post-quantum cryptography on their radar, not even to talk to information theoretic security. That's just a whole nother level that is a little bit far in the future and very ambitious considering the current state and awareness. So there's just been bigger fish to fry, which to me doesn't really seem like a good reason to not advance these protocols and not increase their security and increase awareness. Other experts I talked with argued that trust-based networks would be sufficient. So trust-based quantum key distribution networks. So you would basically need to know personally and authenticate every single node in your quantum key distribution network, which in a research setting is fine. But I think once we're trying to scale the quantum internet, that becomes totally unfeasible and unscalable. So that also didn't seem like a very satisfying answer to me. So basically, the popular approach that everyone just seemed to be satisfied with was building a hybrid network, one where you have a classical communication channel over which you're authenticating the parties to each other via just the usual SSL certificates, the classical means, and then you execute quantum key distribution over the quantum channels. But to me, this seems like it would just completely undermine the additional security offered by a quantum internet if you're just relying on that initial classical authentication, which is just based on public key encryption and conditional security again. So that's kind of where I really wanted to introduce a new spin into the field. And that is where I posed a little proposal. I figured that these trust-based quantum key distribution networks were unscalable, and there had to be a way to introduce quantum-enhanced identity authentication in order to aim for an information theoretic secure quantum internet from an infrastructure perspective. So this is where my proposal came in. I'll just zoom over this from a very high level to try to explain what my idea behind this was. Basically, it's all founded in using certificate authorities, but instead of having them be classical certificate authorities, we have quantum enhanced certificate authorities that can create quantum identity authentication, third-party authentication. So the one that I mentioned at the beginning as an example. So to walk you through what that would look like, the scenario would be, imagine a bank, highly concerned with security, obviously, and generally untrusting of the public insecure communication channels. So this bank wishes to set up their own internal quantum key distribution network to handle their own sensitive data. In order to do this, they need help from the local telecommunications provider because setting up their own infrastructure from scratch with the optical fiber networks and such would just be way too much overhead. So they're relying on the local telecommunication company that already has these optical fiber networks in place to provide that infrastructure while they own their own quantum key distribution nodes and can use the connection, the fiber cables to set that up in their own infrastructure internally. A few years down the line, though, these publicly owned quantum key distribution networks by industry players, and particularly in banking, are pretty common in this hypothetical world. But this bank specifically faces a situation where they want to execute a super sensitive transaction with several other banks. So basically to do this, there's no way they want to do this over the public insecure channels. They want to use their quantum key distribution networks to ensure information theoretic security. There is billions of dollars on the line and sensitive customer data. But the problem is that these other banks that the transaction is to take place with are abroad. So their QKD networks are respectively managed by other telecommunication providers that have nothing to do with the ones that the local bank is using. So the question is, how do we connect these networks? Well, traditionally speaking, and in the view of the researchers that I talked to, the bank faces a couple of options. They could send a representative to each single one of the involved banks abroad to exchange a one-time pad key and then initiate communication once they're back. This is a little bit risky and puts a lot of pressure on this one person traveling with this highly sensitive one-time pad key. It would also be expensive and probably cause some delays if you had to do that with each of the involved parties. Alternatively, the other way that would seem to be pretty popular in research field right now is just using the classical parallel channel. But if an adversary at this point with access to a very powerful quantum machine already knew exactly when the transaction was to take place, they would be able to intercept and basically hack the authentication, and the rest of the whole transaction would be entirely vulnerable without any of the banks knowing even. So my proposal was sitting a quantum certificate authority at the sort of global head of the quantum internet communications. So it's really nothing else than we have today with the certificate authorities. But this authority would be able to execute quantum identity authentication protocols, which are by definition information theoretically secure with the individual parties, no matter where they're located, and authenticate them to each other in this way. The interesting thing about this is that they would really only need to authenticate the critical nodes of each of the individual networks, because within those networks, they'd be able to authenticate themselves. So it would be kind of a one-time QIA third-party protocol between the network's main nodes, after which QKD could commence between them independently. So that's kind of the very high level of the suggestion and the idea. And again, just rewinding, the whole goal behind this was to raise awareness and try to push out some new ideas around the construction of infrastructure and protocol ideation. And I think, especially in this field, there's a lot you can achieve that hasn't been tried before, because the research field is still pretty small. And while the nitty-gritty implementation and researches on specific technologies are super advanced, I think there's a lot of questions around the infrastructure and the future of these networks and protocol design that largely remain unaddressed. So I think it's a super interesting area to delve into. And if you're thinking of doing your thesis in a direction, something like this, I highly encourage you, because there's a lot you can do and a lot of questions that are still remaining unanswered. So that was the overview from start to finish in a very quick way on what I was writing my thesis about. If you have any questions, please feel free to reach out to me at any point. My email is right there. I'm sure Rafa will also, I guess you got the contact information in the link in the sheet of the agenda of today, or find me on LinkedIn. So thank you so much for having me back. And if you have any questions, also let me know.
Thank you so much. It's been amazing. Are there any questions from anyone in the audience? We have some minutes, so we can address several of those.
Happy to answer any later as well if they should come up. Just shoot me an email or a message on LinkedIn.
Okay, seems that it was really clear.
So excuse me, can I talk a moment? Can I ask a question?
Mm-hmm.
So more or less, what are actually the proposed quantum identification protocols? More or less, at least the one that is more suitable or something like that. Some example of it.
Yeah, there's a bunch. There's lots of really different approaches to these quantum identity authentication protocols. Some of them are entirely trust-based. Some of them try to be zero trust and have two parties authenticate each other that have never communicated before. I think those ones are a little bit more questionable to how far those work. I think there's always a level of trust that needs to happen at some stage. But if you're interested in the technical level of like mathematically how they work, I'm super happy to send you a list. I have like a chapter of that in my thesis, and then you can look at which ones you find interesting. If you maybe paste your email in the chat or something, I can send those to you.
I can write it. Wait a moment. I have to open the chat. Here you have.
Cool. I'll send them to you. Maybe you'll find some of those implementations and proposals interesting.
Okay, thank you.
Okay, anything else from anyone? Okay, I think that's mostly it. Thank you so much, Helene, again for delivering the talk. I think it's an amazing topic. We have finished early, so we will leave a few minutes. The next talk is in 15 minutes, so we will leave a small break for everyone that needs it. And in 15 minutes, we will continue with the talks. Thank you again so much, Helene. So good to have you here.
Thanks a bunch.
Thank you.